Let's start with history, or should I say ancient history. The function annotations appeared in Python 3. That was exactly 10 years ago, in fall 2006. And what this is, you can basically attach arbitrary expressions to function arguments and the return value. So these are kind of like docstrings, except for these don't have to be strings, and then you can attach them to any parameters. And this could be anything, like you can fetch an HTTP web page or do database request there, although you don't want to do that. And these are evaluated once. So as soon as the interpreter sees the function declaration, it actually calls, like evaluates all those expressions, and then it binds them to this dict called dunder annotations. And the nice thing about it is you can actually access it at runtime, and it's mutable, so you can modify it. And just to give a few examples, you can annotate the simple arguments like so. So you just put a colon, say x is an int, y is a string. Or you can use default values. You can annotate return value using this arrow, which is dash greater. You can annotate star args, default args, even this funny syntax that no one ever uses for tuple unpacking. What you can't do is you can't annotate the lambdas, because that would break the Python syntax, because lambdas use the colon to separate the args from the body, so you would need like a parenthesis. This would break Python 2 compatibility. Okay, so before we start with the type hints, let's look at a few unconventional examples of what you can do with the function annotations. So you can just use them as comments, as docstrings, and just annotate everything like this. Or maybe you can use them as, for this fancy CLI, like command line API, and it can just provide command options through function annotations. Or you can do something like this. This looks a bit involved, but it's actually just 3 lines of code. So this is a decorator that you apply to a function, and then every time you call this function, it will remember the arguments that you passed and the return value, and will reattach them back as function annotations. And then you call this function, and this is just a screenshot from Jupyter Notebook. And you can actually see, if you press tab, you can actually see the exact values and the return value that were passed. So that's pretty neat. But that's not the intended use case. All right. In fact, just 2 quotes from the PEP back from 2006. So function annotations are completely optional. There were a few people who were concerned about the Python core team just forcing these like static type check and this kind of thing onto Python community. So there were a few concerns. So these are completely optional, and then function annotations are nothing more than a way of just attaching Python expressions to parts of function compile time. So that was it. Okay, so fast forward 6 years. In 2012, there was a new project that emerged called MYPY, which is an optional static type checker for Python. So this was initially a research project by Yuka Lehto-Salo. I think he was doing his PhD in Cambridge at the time. And this was an experiment in gradual typing. And what this is, it's basically a research experiment in, is it possible to do type inference if you just only annotate half your code and not annotate the other, like other code, where the language kind of looks like Python. And initially it worked on a Python-like syntax, which wasn't really Python, but looked more like Cython. So you have like int x, float y, this kind of thing. And then he did a presentation at PyCon Oregon, Portland, I think, in 2013. And there he met Guido van Rossum, who suggested to switch MyPy to use function annotations so that it's actually compatible with Python code. And that's exactly what happened. And then MyPy included this typing module that hosted primitives like dict and list and int and generic type variables and all that. And that was shipped as a part of MYPY distribution. And in 2015, in Python 3.5, there was new PEP type hints, which was largely just based in MyPy. In fact, it was just the typing module from MyPy just moved into the Python standard library. And you can import this in Python 3.5 and onwards. And MyPy now uses the standard library's typing, right? And then these days, MyPy is a fairly stable project with many contributors, including the Python core team and a few people from Dropbox. And it already supports this new Python 3.6 annotation syntax. Now so that's the website, mypylang.org. I would also like to mention that there's a few other static type checkers, and I know at least two. There's Google PyType. It's on GitHub under Google.org. And there's also JetBrains type checker, but it's not open source, and that's what they use for PyCharm. So they have their own, they talked about it, but they would never open source it, right? All right, so let's look at an example of what MyPy is about. So basically, it provides you with vocabulary of like a type vocabulary. So you can say this is a dict, this is a list, this is a dict of ints to strings, like this kind of thing. This is a union, this is a generic variable. And then it analyzes your code without actually running it, so it's an alternative interpreter, so to speak. And it finds inconsistencies in the types, in the past types. And sometimes you have to give it extra help, like annotate a few variables, which is made simpler with Python 3.6. So in this example, we have a function pluck that, so basically what it does, you have a dict, and you give it a list of keys, and then it extracts each element at the given key from this dict, and it converts it to string, then packs it into a list and returns you that. And so the signature is, we say, okay, the data is dict of t, where t is generic type variable, to any, and then the keys must be a list of the same t, so it's compatible with this dict, and then this returns a list of strings, right? And then if we run this, there's a few examples. Like in the first example, the first call side, we pass an a, which is a string, and it's not a list, so it actually gives an error, says the argument 2 has incompatible type. In second example, we have a list, but it's not compatible because it's an int, not a string. So MyPy detects that as well. And the third one actually works fine. And then, so the main point in like using MyPy and is just the simplicity of extending code. And this applies particularly to like huge, large code bases where it's just easier for people to come in and add new code and extend on top of that, knowing that they wouldn't break some stupid things like incompatible types. Now, there's another thing, is that you don't actually have to write tests for this kind of stuff because it analyzes all of your code. So it doesn't matter if some certain branch of your code is triggered or not, it will analyze everything. There's also a price you have to pay. So you have to annotate all your functions. What's even worse, you have to annotate everything else. Because MyPy, like you import NumPy or pandas, and then MyPy has no idea of what those functions mean. And then, so you have to tell it how to interpret the types. And so that's where stub files come in. And so the stub files basically, they're kind of like header files in C. Generally they're just Python code, so you can actually run them, but it wouldn't do anything. And so here's an example from Python builtins. It says true is nothing of type bool, like false is nothing of type bool. And then this is a char function from standard library that takes an integer code, like ASCII code, and returns a string. Now for the standard library, there is a TYPESHED repo, which contains all those annotations for, well, or almost all of them, for all of the functions in the standard library for Python 3.4, I think 3.3, 3.4, 3536. And it proved to be quite a lot of effort to do that, and that's still an ongoing work, completing that. I think that they also plan to publish the type sheds for some popular repos like Request, Flask, Ginger2, and like a few other ones. So normally what you do, if you have a C extension which you can't annotate, or if you have some external code that you can't touch, then you just write those header files, just for the parts that you actually want to use, right? You can also ship those together with your package, especially if you build like Python code or C extensions. Okay. So now the type hints. So as I said, type hints basically migrated from MyPy to core Python standard library in just 1 year ago. These provide standard vocabulary for static analysis. So the point was that we may have many different static type checkers and different analysis tools, but it would be nice if they at least use the same language and could communicate through that. There is a single standard library module that this adds. It's called typing, and you can import that and play around. And MyPy now uses that. And there's actually a PEP on PEP 43, which is a fairly long theoretical document on how these things work, and then how the type variables work, if you're interested. And then just one more quote from this PEP. So Python will remain a dynamically typed language, and the authors have no desire to ever make type hints mandatory, even by convention. And that's again to make people calm and happy that no, Python will not become a statically typed language, right? So it's all just a convention. So let's look at a few examples, and these are all valid MyPy examples, and some of these are taken from the standard library docs. So you can use simple types. So here's a greeting function that takes a string, returns a string, and it looks nicer than a doc string actually because it's part of the function signature, and then so you don't have to follow NumPy docstring convention or Google docstring convention is just all there. So it's pretty self-explanatory. Now you can use there's a few constructs, a few building blocks like dicts, tuples, and lists. So in this example, we have a broadcast message function that takes a message, which is a string, and servers, which is a list of server, which is a type alias. And it's actually a tuple of address and connection options, and address is a tuple of string and int, like IP import. And connection options is dict string to string. And then again, this is fairly self-explanatory, and then you can just see what's going on just looking at these 3 lines of code. And the convention is that if function doesn't return anything or doesn't have a meaningful return value, it returns null, which is exactly what is annotated here. So there's a few more like advanced things like iterators, optional values. So here's the example where, so this is a function that generates squares like 1, 4, 9, 16, 25. And you can provide an end, in which case it just can generate the first n values, or it otherwise deals an infinite iterator. And again, that's exactly what's annotated here, and by using this optional and iterator constructs. And note that in square brackets you have it's basically like angle brackets in C++, so that's your template argument. You can have unions, so you can say, here's a function that checks if the value is positive, and it takes an int or a float, returns a bool. That's exactly what this is. And now there is most of the abstract base classes that you find in collections.abc, like set, sized, hashable, callable, container, mapping. There's quite a few like sequence. And most of them have generic counterparts in typing. And in fact, you can also use them as non-generic objects as well. So you can use those in your like normal non-MyPy Python code, and you can say is instance something set, and set which comes from typing, and that would work. But the difference is that here you can provide a type. You can, instead of saying this is a set, it's now a set of t, where t is or a set of ints. Right. Now, as for generics, so the generics are expressed through type variables, and by default they're invariant. So you can create them through this type var factory. So here we declare a type variable t, and then a function last that takes a sequence of t's and returns the last element. And then the signature is we take a sequence of t and return the t, whatever t is. It could be an int or a float or a string. And there's a few things you can build on top of this, like type variable constraints. So for example, you can have a function that takes a string and takes like a delimiter and splits it into two strings. So if I have hello world and delimiter is w, it splits it into hello world. But the thing is, this would work with a bytes object and a string object just equally well. However, you can't supply string as the first argument and bytes as second argument, because it will throw an error saying, you know, they're not compatible. You have to either Unicode decode one of them or the other. So what we do here, we introduce a type variable, which is any str, which is either a string or bytes. And in this function declarations, this type variable must be either string or bytes. So it's not a union. It has to be. So all four of those instantiations of this type variable have to be either a string or bytes, right? In fact, this is so common that this any string is actually part of typing. And there's like a lot more than I've covered here. In you can specify upper bounds. You can define generators. You can create generic classes with generic methods and all that. But there's a lot of syntax to cover, which is not the point of today's talk. Okay, so variable annotations, just really brief. So this is new syntax that was introduced in Python 3.6 that will land in 6 weeks from now, I think. So basically, in MyPy, to annotate a variable, to just help the type checker figure what your variable is, you would use this comment, and you would do the same thing in Python 2, by the way. You would use a comment with a special syntax, and let's say type, colon, and then you just provide a type, and then it evaluates that. So now it's actually part of Python syntax, so you don't have to use comments, and you can say primes colon list of ints equals empty list. What's more, you can actually create annotations for uninitialized variables. So this wasn't possible before. So previously you had to say name equals ellipsis, but technically the name is bound to a local variable and then it's actually equal to ellipsis, which is a Python object. Now we can just say name colon str. And if you try to access name, it will give you an unbound local error or something like that. So it doesn't exist yet. So that's nice, and it would make a lot of like MyPy compatible codes like a lot cleaner. And then finally let's talk about runtime type checking. So the question is, could we use the same building blocks, the same vocabulary, which is very nice and like really well thought through? Can we use this at runtime? And hypothetically, you would have something like this. So you have some function that takes maybe an int or a float and then squares that, returns it. And it would be nice to have a decorator that actually checked the type of the input value, and then you would like raise a type error if there's a mismatch. And the question is why? Like why would you want to do that? There's MyPy, there's PyType, there's all those tools. And there's a few reasons. So first, the static analysis is very good, it's great, but it can be a huge commitment. So if you try to convert your unannotated code base to use MyPy, you would spend like weeks of time, if not more, trying to annotate everything, and then you would have to annotate your C extensions and build those stub files and all of that. And then you would probably have a lot of errors, and then you would go and fix all of them. So trying to go from 0 to 100% with static analysis is pretty hard. And then another problem is that static analyzers don't actually run your code. So if you're being too smart with like meta classes and stuff like that, then this could trip them up, and that's what happens. And so and the third reason is maybe you don't want to depend on external tools. You don't want to depend on someone having to run MyPy or PyType on your source code. And here's just a very quick example that makes MyPy fail. So you have, so maybe you want to impress your coworkers, and you have this fancy name tuple, which you can create using square brackets and not parentheses, which is a great win, right? And it actually works. It's valid Python syntax, just requires 3 lines of code to make this work. Just requires to set a meta class, which has get item. But MyPy doesn't like it because it thinks it's a generic type, and it knows that point is not a generic type from MyPy's point of view. So that's, and that fails. And that's just one of the examples where it wouldn't work, like in case like this. Another thing I've noticed is that this is a very typical snippet that you find like everywhere, right? So you do something, and then first, like, it's Python, so you're not sure what did you get. Maybe it's an int, maybe it's, I don't know, maybe it's module or a dict. So you've been safe and you check the type, and then you do something. And then so I did a little search on GitHub and found quite a lot of examples. And that was 3 days ago, so I think now there's more. And then I went through the first page of this query on GitHub and tried to convert it, the examples, to use like a saner or shorter syntax. And this is just completely random code that I'm not familiar with at all. So this is some operator, call decorator operator that looks like a method that takes arguments, which looks like a tuple, and both elements are data.int, right? And this is quite hard to read because it's a lot of code. What you could do instead, you can say, all right, this argument is a tuple of data int and data int, and just remove all those like if is instance stuff, right? And this is self-explanatory, and it also works as a docstring. Okay, the next one is define dunder new. So this looks like a factory, like instance creation function in a class. It takes a class expression and ls, and expression is surprisingly an expression, and then ls is an ls. And then we call class.make, which supposedly will not do these checks. And then again, it would be nice to just do that, because that's exactly what we imply. And the third one is, this is some scientific code that this is some setter for priming variable, priming property. And it checks that the value is not none, and then, or it checks that it's either a none or data source. But to infer that, you kind of have to reverse this if and read it like that, right? And what it actually means is that value is just an optional data source. That's all it is, right? And then this is just a one-liner, basically. So there's a few problems so why is it hard to build a runtime type checker? So first is this: we don't observe types, we observe classes at runtime. And there's an unfortunate naming in Python, so for example, list is a class, right? Now, list, capital list of union of int float is a type. To add to the confusion, type actually returns a class, not a type. The type function. But the type creates classes and not types. And some types are classes, and classes are observable at runtime, but types are not observable at runtime, or not always. Like, what's the type of an empty list? Is it a list of ints or a list of lists of ints? And static analyzers don't care about this. They don't run your code, so they just assign types to variables in this crazy type graph, and then that's it. However, the runtime type checker has the values, and then you can only observe the classes. And then so you can only work with that. Challenge number 2, it's iterators, generators, callables, lazy objects. So you can't type check that at the call site. So if you have an iterator and you consume it to check the values, then it's dead, it's gone. So you can't do that. If it's a callable, and then you can just call it to check what it's going to return. So you can kind of sort of defer that. You can say, okay, we can take an iterator and we can provide you a fake iterator that actually injects the type check into it, but then that gets very complicated very fast. And this will require creating object proxies for like everything. And so that's just an example. Maybe your object is a stream of ints from file, and then your function requires an iterator of ints. So what do you do? And the third one is this. Now, because I'm a quant, I'm obsessed with performance, and like for me, a microsecond is a lot of time. There's a few existing runtime type checkers in PyPy, and the overhead for checking a trivial function that takes like 400 nanoseconds is about 40 to 90 micros, which is a lot. I can do like a lot of stuff in 40 microseconds. It's like an eternity. And ideally, you would have something like these two snippets should be almost equivalent in runtime. So if you want to check that x is an int, we should just check that it's an int, and then that's it. Maybe call one function or two functions. So it's an overhead of calling like maybe two function calls at most. And then, so I spent like a few maybe weeks like just building a prototype to see if it could work potentially. So there's a work in progress. It's on GitHub, which do we have a few minutes to yeah. So we can probably check it out. So that's a little package that looks at the type hints and actually generates the code that checks that, which looks exactly like the previous example. And it does support invariants, type variables, constraints, upper bounds, and supports some of the typing modules. Maybe let's try to take a look. Is it? So that's just like in a Python notebook. Okay. So there is a type check decorator, and so let's check this function that takes an int and does nothing. It has a docstring. So let's try to call it with an int, and that works fine. Or like with a 2, that works fine, and it's not. Okay, well, it gives you an error saying invalid x, expect an int, got a float. What you can also do, you can see the code that it generated, right? And that looks exactly like the. I'm sorry, larger. Is it good? Okay, so that's the code that was actually generated behind the scenes. And there's a few like injected variables in this context as well. But that's basically it. That's 3 lines, and that runs. That should run like very fast. It's like 490 nanoseconds. Whereas like if you run it through the other PyPy examples, like packages, that would be at least 50 micros. Okay, so let's look at an example with type variables. So here we have a type variable that's either an int or a float. And we say, okay, type check a function that takes a t and a sequence of t's, right? And so this is valid. So g of 1, 2, 3. So because 1 is an int, 2 and 3 are ints, so that works. Now you can also use a tuple, for example, not a list, because it's just an instant in sequence. So these are floats. This also works. Now, if this is a float, but this is an int, then this should fail, and it does. And it actually tells you where it fails. And so it works. The thing is, it actually generates quite a lot of code. And this is it actually generates a type inference engine, which is based on your on the signature that you provided. And this may look like quite a lot of code, but it actually works very fast because most of this code is never reached. It's only reached if something fails. And let's just look at one more example. So this is a function that takes an int and a sequence of ints, and then multiplies each element by this factor and returns a list. Right? So and let's see how long it takes to run that. So let's multiply 1, 2, 3, 4, and should be fairly fast. And it takes 1 micro. And then let's do the same thing where we actually check, where we manually check all the types. We check, okay, this factor is actually an int, and each element is an int. This array is actually a sequence. If we do this manually, It takes 4.37 micros. Now, if we do the same thing with this decorator, 1, 2, 3, 4, it's actually faster. Well, it's because it's cheating and caching some things internally, but it is faster, so that works. And just as an example, so this is one of the packages that I found on MyPy. This takes like 80 micros, so it's a lot slower. And now this will, in this example, quite a lot of code is generated, but not too much. And you can actually read through it, and it kind of makes sense. It checks that your object has an iter and get item and a len. Is it sequenced? Then it goes through it and checks each single element. And then if everything is fine, it just returns you the value. So that's so this is available on my GitHub as a typo package, and so here's the link. And thank you for coming.
Type annotations are good with simple examples, but what's your opinion about more bigger examples? Have you used, especially with object-oriented programs, the function signature could be very big, and also you lose lots of readability. So what's your opinion?
Okay, yeah, thanks for the question. So my whole point with chasing performance here is that it should be almost as fast as you just doing things like if is instance int, if is instance float, just checking things manually. And this thing's already all over the place in like a lot of Python code. So this just basically removes the need for that. It doesn't, validate your data. It doesn't do anything else. Also, the generic types, checking for generic types may take longer. Checking for basic types is very fast.
I'm not talking about performance. I'm not talking about performance. I'm asking about how you could read the code. If it is more understandable, or you lose the ability to understand that code.
You mean the type hints? Yes. So that's not related to my package at all. That's like a general type hints question. So they're not meant to be used in place of docstrings, but rather to support the docstrings. But rather than encoding your types in the docstrings like we currently do, like in NumPy convention, Google convention, and Sphinx parses that. So this is just another way of encoding that in function signature. And I think it's very expressive. If you go through the typing module, there's a lot of building blocks that you can use. we can talk after.
Okay.
Yeah. You briefly mentioned abstract base classes during your talk. So I was wondering, using either the typing module or your library, is there anything to implement something a bit like a Java interface? That is to say, you have a blank method with a certain type signature, and you ensure that whatever class implements that ABC also adheres to that type signature.
Yeah, that's completely possible. In fact, the typing module provides this generic, like capital generic class, which serves as a base class for any generic classes that you implement. And then, so there is machinery to support that, so it's completely possible, yeah.